right, this is the intro video for section 3.1 for AP Calculus AB. And we're going to be focusing on extrema for most of chapter 3. And so that's where we're going to start here. So finding extrema, definitely an important concept. Finding minimums and maximums, finding where something is increasing or decreasing. These are all key concepts to help us find maxes and minimums. So a couple of blanks to fill in here. Extrema would be another way of saying a maximum or a minimum. So if you're asked to find extrema, that's just another way of saying find a maximum or a minimum value of a particular function. Let's take a quick look at this box here. It's just a formal definition of maximums and minimums. So take a look here at number 1. It's saying f of c is the minimum value of f on a particular interval if f of c is less than or equal to f of x for all of the values of x in the interval. So in other words, if f of c is smaller than or equal to all the other values of f of x, then f of c must be the lowest value, making it the minimum. Well, of course, number 2 is similar. The only thing that's different is that this is a greater than or equal to instead of a less than or equal to. And so, we think of a maximum as being the highest point on an interval. That means that it is as high or higher than all the other points on that same interval. A few other things to go over here. We'll move out of the box at this point. It says, next little blank fill-in says, extrema on a closed interval can also be called absolute or global extrema. So those two terms are interchangeable, absolute or global extrema. Both of those are describing extrema on a closed interval. So that's going to be a situation where we're given just a limited domain. Right from -5 to 12 or something like that. You're going to have just a very specific interval. If you're trying to find the extrema on that closed interval, we're going to call them absolute or global extrema. Absolute extrema will happen at one of the endpoints or what we call a critical number. So the endpoints would just be the endpoints of the interval. Now let's talk about what a critical number is. C is a critical number if f prime of c is equal to 0 or if f prime of c is undefined. I want to try to connect this back to some stuff that we did in chapter 2. Maybe you'll remember the homework, maybe you'll remember some of the things we had in the notes, maybe even a test or a quiz. When f prime of c is equal to 0, f of x has a blank at x equals c. Take a second and try and think about that. Think about what would go in the blank. Of course, the answer is f of x has a horizontal asymptote. So we're still going to be working with that. We're just going to be using those places of horizontal asymptote. We're going to be calling them critical numbers. We're going to be using those to help us find the extrema. We're going to take a look at this graph next. All right, I want you to, like it says here in the instructions, I want you to look carefully at this graph, and I want you to try to label the critical numbers. I want you to label the places where it appears that this graph has a horizontal tangent line. So let's do that first. Feel free to pause the video, do this on your own. I'll do it up here. So I'm seeing horizontal tangent lines right here. Looks roughly at x equals 0. And then over here, maybe x equals 2.5 or something. I guess we don't know the scale exactly. And just by way of review, let's remember a horizontal tangent line would look something like, let's try that other one again here. Looks something like that. There we go. And so those are two places where, in my opinion, hopefully you share that opinion, looks like that graph has a horizontal tangent. I'm going to go ahead and erase those little tangent lines real quick. And we'll work with this a little bit more. So the other thing the question asks us to do is to consider where the absolute extrema are located. Remember that absolute extrema will happen at either the critical numbers or the endpoints. So we'd simply be looking for where is the y value highest and where is the y value lowest. So again, I'd encourage you maybe to pause the video and think this over to answer that question. Where would you find the absolute highest y value on this interval, and where would you find the absolute lowest y value? All right, so we've got two critical numbers there and there. I'm going to go ahead and label the endpoints with green, right here and the other endpoint would be over here. So where's the highest? Where's the absolute highest point? Well, I think we can tell pretty quickly. We're just looking at where the highest y value is. I would say that the highest y value would be right there. That would represent the max. I don't see any other point on that graph, on that interval, that is a higher y value. And then the minimum would happen over here. Again, I don't see any place on that graph that has a lower y value than this, this point over here. So maybe what's something interesting to think about here is that you can see that the maximum actually happens at a critical number, right? That's a place where f prime of c equaled 0, but the minimum happened at an endpoint. So there's great flexibility here. You could have the maximum and the minimum both happening at endpoints, or they could both happen at critical numbers, or could be a mix like this one here. Like I said, we have a lot of flexibility as to where those maximums or minimums could occur. All right, we are going to finish by talking about what's called the extreme value theorem. This is a very simple theorem. It's an existence theorem. It doesn't really tell us what to do. It just tells us that something exists. So take a look at it. It's up here. The extreme value theorem, if f is continuous on a closed interval AB, then f has both a minimum and a maximum on that interval. So there's some examples here that I think are worthwhile to illustrate this extreme value theorem. The first one, we'll call this one number 1. You can see that we have a closed interval, right, from -1 to 1, from right here to right here. You can see that on that interval, there are no jumps, vertical asymptotes, no removable discontinuities. It's continuous, right? We can look at the graph and reasonably say that that's probably the case. And so the extreme value theorem tells us that we have both a minimum and a maximum. And you can see right up here, we got a maximum there at 2, 5. It's the endpoint, and we have a minimum right here, 0, 1. That, of course, is a critical number. You can see that's where we'd have a horizontal tangent line, and so that would be our minimum. But because, again, this function over here is continuous on a closed interval, it will have a minimum and a maximum. You can see that that's not the case with graph number 2. You can see that the endpoints here and here both are open, and so that this particular function is not continuous on a closed interval, so we are not guaranteed that we will have a minimum and a maximum. And you can see that we do still have a minimum, right? It's right here. It's that critical number again. But this is not a maximum, right? Because it's an open interval. And if you remember, what that open interval symbol means is that the function isn't there. It gets as close as possible to that point, but it doesn't actually reach that. This would be a place where, I think a reasonable person would say, well, what about this point right here? Isn't that like really close? Wouldn't that be the maximum? Well, if you're going to consider that, what you're really doing is you're redefining the interval to be a closed interval, right up there, real close to x equals 2, and you've completely changed the question. So this goes back to that extreme value theorem. If f is not continuous on the closed interval, then we don't know for sure that f has a minimum and a maximum on that interval, and we can see with graph number 2 that in that case it doesn't have a maximum, even though it does have a minimum. And then the final case down there, you can see once again we've got a function that is not continuous on the closed interval. We can see that right here we have a removable discontinuity, and then we get this point up here. This is a clear point of discontinuity. So the extreme value theorem doesn't really tell us that this should have a minimum and a maximum. It could, but the extreme value theorem needs to have continuity on a closed interval to guarantee both a minimum and a maximum. We can see that this one does have a maximum, right, on that endpoint over there, 2, 5. But what used to be the minimum is not the minimum anymore because the function doesn't exist right there, right? Doesn't exist. And so, once again, we're not going to redefine this to be, a new closed interval. We're simply going to say that there's not a minimum here because of that lack of continuity. So again, it's an existence theorem. We really can't use this to find something. It just explains what may or may not exist. I think it's important for us to realize which topics or concepts are going to kind of weave themselves throughout the year, things that are just not going to go away. And one of those is a critical number. So I thought I'd throw it in here at the end of the video again, just the definition of a critical number. If f prime of c is equal to 0, or if f is not differentiable, at that particular value of C, then we say that C is a critical number of F. Once again, that'll help us find minimums and maximums, and we'll use it for all kinds of other things as well, applications and so on. But I thought I'd leave you with that for now. I'll see you in class next time, and we'll do some work with the examples coming up.